All right, so today we're going to look at lecture 5.2, and topic 5 is focused on integration of equations. So we're going to look at another rule. So last class we looked at trapezoidal rule. Today we're going to look at Simpson's rule. And there's two Simpson's rule. One is called 1/3 and one is called 3/8. So we're going to look at both of them. The main difference between trapezoidal and Simpson's rule is in trapezoidal, we try to draw trapezoids between 2 points. In Simpson's rule, we try to fit a polynomial between every 3 points. So that means every time I apply the Simpson's rule, I'm looking at 2 segments. So for example, if I had 3 points here, so let's just say this is 1 point, this is another point, and then this is another point, and they're equally spaced, all right? And we're fitting a line or a polynomial, so a second order kind of polynomial between 3 points, right? Because if you have 3 points, then you have a second order polynomial. And what we're getting is that we're looking at the area below this polynomial. And we're estimating by integrating this polynomial that that's the area below the actual function or line or point that we have. So sometimes you miss areas like here, and sometimes you're adding areas like here. But overall, this is more accurate than the trapezoidal rule. Any questions on this so far? So the 3/8 rule, instead of using 3 points, we're going to be using 4 points and then fit 4 points, essentially. And we'll see why it's called the 1/3 rule in a second when we have 3 points. So we're going to look at deriving the actual equation for the 1/3 rule. So we're going to write Simpson's 1/3 rule. And again, we're forming a second order polynomial. So I'm just going to write it down. So second order polynomial using 3 points. So last class, we also looked at fitting polynomials to points. Do you guys remember which method we covered? No idea. So it's called Lagrange, right? So using Lagrange, we can fit these 3 points and then integrate the Lagrange polynomial and then come up with a general expression for this approach. So we're going to be integrating, so I is the integral, from x0 to x2. So that means if I'm looking at this graph here, this first point is x0, second point is x1, third point is x2. So I'm integrating from x0 to x2, but I have 3 points, so that's why we're skipping one when we write this integral. In here, we're going to write down, the actual Lagrange polynomial. So for a second order polynomial, do you guys remember how many weights I had in the polynomial? So it's second order. You have 3 weights. You have 3 total weights, but every weight has how many terms? 2 terms. So in here I have 2 terms, like that. And then we have our first point. So the value of f at the first point. So fx0. So this is a bit of review also for what we did last class. And we have a second point here. So second weight and the second point, so x1. And then we also add the third point. So f of x, 2 in this case. So if you remember, on the top left, we always had x, right? So x, x, x. And then on the bottom left, we always had the x that we are using the y value of, right? In this case, it was called also I. So in the first one, I is 0. So we would put on the bottom left, x naught here. On the second one, we have x1. The third one, we have x2. Then for the values that we're subtracting, we used something called the j, right? We called it j values. And j was never equal to I, right? So in this case, if I is 0, then j would be 1 and 2 in the first one. So this would be x1, x1, x2, x2, right? Second one, do you guys remember what this would be? Right. So x0 or x0 and x2. And then the last one would be, right, x0 and x1. So this would be the polynomial that we're integrating. I'm not going to do the integral, like I'm not going to expand this out and integrate it. But essentially what you get, if you do the math, is h, which is the step size, right? Which is, basically the difference between x0 and x1, right? Or x1 and x2, divided by 3. So this is where the 1/3 rule comes from. The coefficient here is 1 over 3 times h, multiplied by f of x0 plus 4 times f of x1 plus f of x2. So that whole thing on top, after integrating, comes up to this simple equation. And this simple equation is Simpson's 1/3 rule. In this case, the h, right, is equal to what? The step size. The general one was b minus a divided by n, right? So in this case, it would be minus a, but n is equal to 2. So instead of n, we can just write 2. So in general, for the Simpson's 1/3 rule, where we're applying it a single time, this is the equation that we would plug in here. So that's the h that we would plug into the equation. Any questions so far? All right. So just like in the trapezoid rule, we're also going to look at what's the error for the 1/3 rule in general, so that we understand kind of its limitations and advantages also. So the error in this case for the Simpson's 1/3 rule, for a single application, because we're also going to do multiple applications of the Simpson's rule, is going to be ET equals to 1 over 90, negative 1 over 90, h5, or h to the power of 5, multiplied by the fourth derivative at xi, where xi is, between a and b, a value between a and b. If I plug in h in here, right, h is what? B minus a divided by 2. So I'm going to do b minus a to the power of 5, and also 2 to the power of 5. So then I end up with, in the denominator, 90 times 2 to the 5. All right? And this is going to basically be a very large number, which is 2,880. All right? And this is going to be b minus a to the power of 5. And then we're going to have the fourth derivative at xi still there. So looking at this equation, right, if h is large, then I'm going to have a large error. So same as before, you decrease the step size, you get more accuracy. Another thing, if the fourth derivative is small, then also my accuracy is large, right? When is the fourth derivative equal to 0? Come on, it's an easy question. When is the fourth derivative equal to 0? Like if I have a linear equation, the first derivative is a constant, second derivative is 0, right? So when is the fourth derivative equal to 0? Right. So when I have a third order polynomial, then my fourth derivative would be 0. So in that case, essentially, this method is third order accurate, right? So the error is proportional to the fourth derivative. Therefore, it is third order accurate. So what does that mean? It means if I have a cubic equation, then the value I get for the integral would be an exact value. So if the function is cubic, then I would get an accurate or an exact integral. Which also applies if it was second order or first order. All right, so now we're going to do an example, and we're going to do the same example we did last class. So last class we did the trapezoid rule using a function. Now we're going to do the Simpson's 1/3 rule using the same function and looking at the difference in the results. So in this example, we're going to use Simpson's 1/3 rule, and we're looking to find the integral from 0 to 0.8 for the function 0.2 plus 25x minus 200x squared plus 675x cubed minus 900 x to the 4 plus 400 x to the 5 dx. So looking at this integral, again, kind of practice from last class, what's a? 0. So that's our starting point, and we see that in this integral right here. So what's b? 0.8. So what's h in this case if we're using the Simpson's 1/3 rule? 0.4, right? So it would be b minus a divided by 2. So that would be 0.8 minus 0 divided by 2 equals 0.4. So if I'm looking at the equation here for the Simpson's rule, I need x0, x1, and x2, right? So let's write that down. So we have our x0, we have our x1, and we have our x2. So we know x0 is 0. We know x2 is 0.8. So x1 would be a plus h, right? So 0 plus 0.4. So this would be 0.4. So now I can write down the equation, right, for the Simpson's rule. Again, it's h divided by 3 fx0 plus 4 times f of x1 plus f of x2. And then we can plug in, right? In here, we have x0 is 0, x1 is 0.4, and x2 is 0.8. Then you have to plug these values into the function up here, right? And evaluate what their value is, and then plug it in and then get a value. So if you do all that math, you're going to get 1.367467. You probably don't remember what we got last class, but last class when we used the trapezoid rule, we actually got a value of 1. All right? And the true value, the exact value, is 1.640533. So you can kind of see that we got closer to that exact value, right? Using the Simpson's 1/3 rule, applying it one time. All right. So the error here, the true error, is 0. Is it 0. Yeah, 0.273, and the true relative error is 16.6%. All right, so now what we're going to do is look at how can we apply the 1/3 rule multiple times, within one single kind of graph. So we're going to look at Simpson's 1/3 rule for more than 3 points. And how do you think that would look like? If I have more than 3 points, how do you think the Simpson's rule would apply? Right. So the sum of multiple integrals, right? So basically, we're basically adding this term multiple times, right? So in that case, it's going to look like I equals integral x0 to x2 f of x dx plus, what's the second integral going to start from? From x2, right? Because we're building on from there, and it'll go to x. So it's 3 points. So x2, x3, x4. So this would be 4 f of x dx plus, actually we can just write the general form now, plus, xn, and this would be xn minus 2. Okay, and then f of x dx. So that's the general form. Now what we're going to do is look at how can we derive an expression that will be simple for when we're applying more than 3 points. So we're going to use a graph again. We're going to use kind of the same graph that we did just now. And what we're going to do is have multiple points on here, starting with x0. All right, x1, x2, going all the way to x6. Just take some time here. All right. So we're going to do, in this case, how many segments? 6 segments. So we have 1, 2, 3, 4, right? 5, 6. And every 2 would be covered by one application of the 1/3 rule. So in this case, we're going to have the integral I is going to equal h over 3 times f of x0 plus 4 times f of x1 plus f of x2. So that's covering the first 2 segments, right? Then we're going to add to that the second part, so h over 3. And in this case, we said we're starting at x2, right? So f of x2 plus 4 times f of x3 plus f of x4. And then we add one more, plus h over 3. In this case, we start at f of x4 plus 4 times f of x5 plus f of x6. So looking at that, we can see that some terms are used more than once. Others are used just one time, right? And some of them are multiplied by 4. So do you see the pattern here? Which ones are multiplied by 4? The odd numbers, right? So odd numbers would be multiplied by 4. The even numbers are repeated, right? So if we look at how are they repeated, so if we look here, this is the first kind of Simpson's application. x0 was used one time. x1 was multiplied by 4, x2 was multiplied by 1. But then in the next one, right, it was also used one time, x2. x3 was multiplied by 4, x4 was multiplied by 1, but also again used in the next one. So 1, 4, I think I made this too small here. Just go all the way to here. So 4 and then 1. So the first starting point was used one time. x1 was used 4 times. x2 twice. 4, 2, 4, 1. Does that make sense? Right? And in general, just to kind of complete this expression here, you know, plus h over 3 f of x plus 4 times f of x plus f of x n. So if the last point is n, right, then the one before it will be n minus 1, and the one before it will be n minus 2. All right, so taking all this expression and summarizing it using the odd and even values, what we get is I equals to h over 3, because that's kind of the coefficient for all of them, multiplied by the initial point, f of x naught, right, plus the summation, or 4 times the summation of all of the odd numbers. So we're going to say I equals 1, 3, 5, and so on. All the way to what? N minus 1, right? Because that's what we see right here. So we're going to write n minus 1 here, and f of x, I, plus 2 times the summation of all of the even numbers. So this will be j equals 2, 4, 6, and so on, all the way to n minus 2. So this would be f of x j plus the last point, right, which is f of x n. So this is the equation for multiple applications of the 1/3 rule. And the error in this case is EA, approximated error, is b minus a to the 5 divided by 180 n to the 4 times f average fourth derivative. So the average fourth derivative, we kind of covered that last class, right? I don't know if you remember, but this was equal to the integral from a to b of the fourth derivative, right? At, you know, xi or x divided by b minus a, right? So in this case, you know what, I'll show you why this is the reason. So in fact, you know, this is the average. So what is the average? The average is the sum of something divided by how many points you have, right? So kind of like side note here, a side note. What we have is the sum of the fourth derivative, right, divided by n, right, which is the number of points that we have, or the number of segments, sorry. So in this case, actually no, n is the number of points that we have. No, segments. All right, so if I look at a graph of f to the 4, x, and this is x here, and say it's some type of graph, kind of like whatever, it looks like that. What we said is to approximate this, we're taking the integral and dividing by b minus a. How does that look like? That looks like this. So we have a here, we have b here, And what I'm doing is I'm taking this integral and I'm dividing by b minus a. What does that mean? This integral here is what? It's an area, right? Typically area, if I'm looking at a rectangle, is equal to what? Length times width, right? The width here is what? B minus a. So the length is equal to the area divided by the width. So the area is the integral. The width is b minus a. So we're approximating the average, right, using this approach. Does that make sense? So in general, you guys don't really need this for the course, okay? I'm not going to ask you to evaluate this error, maybe in an assignment, but not in a quiz or a midterm or a final, okay? So no, you don't have to derive it. But I'm just showing you, like, in case maybe you go to grad school or you go to some advanced course, you kind of see where all this comes from, okay? All right, so we're gonna do one example, all right? And then stop there. So, and then the Simpson's 3/8 rule we'll cover next class. So what we're gonna do is we're gonna do the same example we just did and try to see if we can get a more accurate estimate of the integral when we apply 4 segments instead of 2 segments, all right? So example, and we're going to repeat previous example with 4 segments, okay? So what's n in this case? N is equal to 4, right? So if I say on an exam, I want you to use 4 segments, okay, know that n is equal to 4, okay? Technically, if you ask me, I'm not supposed to tell you, all right? So from the previous example, A was 0, B was 0.8. So in this case, H is going to equal to B minus A divided by N, which in this case is 0.8 minus 0 divided by 4. So instead of 0.4, we have an H of 0.2. So if we want to look at the points that we're going to be using in this case, right, we can just draw a line and start with the first point. So the first point is 0, right? What's the second point going to be? 0.2, right? So we add h. Add h again, we get 0.4. Add h again, we get 0.6. Add h again, we get 0.8. So these would be our, x0, x1, x2, x3, x4. So when we look at the equation right here, this equation, now we can evaluate which one's odd, which one's even, right? And know where to plug it in. So we're going to write I equals h over 3. Again, starting point f of x naught plus 4 times the sum of the odds. So I equals 1, 3, and so on if we have more. 2n minus 1. In this case, n is 4. Right? So then n minus 1 would be 3, right? So we're only going to have I equals 1 and I equals 3. Then we're going to add to that 2 times, sorry, before adding that, we're going to need to write what it is. This is called f of x I plus 2 times the sum of the evens. So we're going to have 2 up to n minus 2. In this case, n is 4, so then n minus 2 is 2. That means we're only going to have one even number, and this is going to be f of xj plus the last point, which is f of xn. All right, so looking at what we set up right here, we can easily know which ones are x naught and the next one and so on. But let's just go continue with this. So h is 0.2, so we can write 0.2 divided by 3. F of x naught is 0, so we can write f at 0 plus 4 times. So we're going to have two terms now. We're going to have I equals 1 and I equals 3. So I equals 1 is f of x what? F of x1, right? So what's that? 0.2 plus f of x 0.6, right? Because that's x at 3. And then we're going to add 2 times f of x2, which is 0.4, plus the last point, f at 0.8. So this would be our integral using multiple applications. Again, you would plug in the 0 to the equation, that we have all the way up here, right? And then you plug in 0.2, you plug in 0.4, and so on. You do all that math, and then you'll end up with a value for the integral, which is 1.62467. The error here, the true error, is 0.017067, and the true percent relative error is 1.04%. So we can see that we jumped, right, from, what was it here, 16%, right, 16.6% true percent relative error, all the way down to 1%, right, by just applying an extra application of the Simpson's rule within that kind of span in that plot. Any questions? All right, so I'm keeping it short today, so that's it for today. Next class, we'll look at Simpson's rule, and then we'll look at the Romberg integration methods.